The most difficult question in science is not just how life works, but how it began. Because at some point, lifeless matter became something that copies itself, evolves, and feels. Panspermia emerges as a bold possibility. Life may have arrived here already in the form of seeds. Think of meteors as delivery capsules from the universe. The Earth was bombarded by space rocks for millions of years, especially in the beginning. If some of these rocks carried organic molecules or even resilient microbes, they would have been the perfect male to initiate a biological process. But the theory does not necessarily say that life came ready-made. There are different versions. Some talk about complex molecules, others about microorganisms. The central point is this: the universe may be a place where organic chemistry is common, and Earth may have received decisive ingredients from outside. When we talk about the ingredients of life, we talk about carbon, hydrogen, oxygen, nitrogen, phosphorus, sulfur, and mainly organic structures that form amino acids and DNA bases. The surprising thing is that these building blocks are not rare. They appear in meteorites and interstellar clouds. By observing space, scientists detect chemical signatures of organic compounds in regions where stars and planets are born. This suggests that prebiotic chemistry may occur even before a habitable planet exists. Life, then, would be less of a local miracle and more of a distributed phenomenon. Comets are another central character in this story. They are icy bodies that preserve ancient material from the solar system. When they pass close to the sun, they release dust and gas. If this dust contains organic molecules, it can seed worlds. It's as if comets are the gardeners of the cosmos. It's not just poetry. We have already found evidence of amino acids in meteorites and organic compounds in comets. This doesn't prove life, but it proves potential. Because if the building blocks are available, the question becomes another. How many times does the universe try to assemble the puzzle of life? Here begins the most controversial part. Could microorganisms survive in space? Space is cold, dry, with intense radiation and a vacuum. It seems impossible. But life on Earth has surprised science several times. There are extremophiles that live in conditions reminiscent of other worlds. In the ocean depths, near hydrothermal vents, life thrives without sunlight. In deserts, bacteria survive with almost no water. In radioactive environments, some withstand DNA damage. If life can endure here, perhaps it can withstand more than we imagine outside of here, for a limited time. The resistance to drying out is especially important. In space, liquid water does not exist in the way we know it. So if a microbe were to be transported, it would have to enter a dormant state, almost like a pause in life. Many microorganisms do this when the environment becomes hostile. Bacterial spores are an example. They can remain inactive for long periods and wake up when conditions improve. Microbial panspermia relies on this ability to survive launch, space, and re-entry. It seems like a sequence of absurd obstacles, but each one has possible loopholes. The first challenge is to leave a planet. Giant impacts can eject rocks into space. This has already happened on Earth and Mars. We have meteorites on our planet that came from Mars, identified by their chemical signature. If rocks travel, the question becomes, can they carry protected life inside? The interior of a rock is a natural shield against radiation. It is not perfect, but it reduces damage. If a microbe is in internal microcracks, it may receive less radiation and fewer extreme thermal variations. This creates a window where survival is unlikely, but not impossible. The second challenge is to fall into another world without being destroyed. During re-entry, the surface heats up a lot, but the interior can remain relatively cool for a few seconds, depending on the size of the rock. So, paradoxically, a meteorite can sterilize from the outside and still protect on the inside. The capsule burns, but the contents can escape. For this reason, Mars is always mentioned. It is close, had water in the past, and suffered huge impacts. If life first emerged on Mars, it could have been transferred to Earth, especially when both worlds were young. Panspermia, in this case, would be interplanetary, within the same solar system. The primitive Earth was chaotic. Volcanism, oceans forming, frequent impacts. It is possible that the chemistry to generate life was repeatedly interrupted. If some biological material arrived from outside at the right moments, it could have accelerated the transition. Not as magic, but as a catalyst. Another version of the hypothesis is chemical panspermia. It does not refer to microorganisms traveling alive, but to complex molecules that facilitate the emergence of local life. For many scientists, this version is more plausible, as it avoids the biggest leap of the theory: biological survival in space for long periods. The space is cold, dry, with constant radiation and practically no protection. Cosmic radiation damages molecules, breaks DNA, and prevents reproduction. At first glance, surviving there seems impossible. But life on Earth has already shown that impossible is a dangerous term. On Earth, there are organisms called extremophiles. They live where it seemed there was no chance of life at all. Some thrive in extremely high temperatures, others in extreme cold. Some withstand acidity, salinity, and radiation far beyond what we considered tolerable. In deep hydrothermal sources, life exists without sunlight, powered by chemical energy. This has shown that life does not necessarily depend on pleasant conditions. It depends on energy, minimal stability, and time. This point completely changes our intuition about where life may exist. Another crucial factor is resistance to drying out. In space, liquid water does not exist. Therefore, to travel, a microorganism would need to enter dormancy. Many do this naturally when the environment becomes hostile, practically pausing their biological processes. Bacterial spores are an extreme example. They can remain inactive for long periods and wake up when conditions improve. Microbial panspermia relies precisely on this ability, to survive without metabolic activity during the journey. But how would these microorganisms leave a planet? Giant impacts are the most plausible answer. Asteroid collisions can launch rock fragments into space. This has already happened on Earth and Mars, especially in the first billion years of the solar system. We know this because we have Martian meteorites on Earth. They have been identified by their chemical and isotopic composition. This proves that the exchange of material between planets is real. The question is not whether rocks travel, it is whether something alive can travel protected within them. The interior of a rock functions as a natural shield. It reduces exposure to radiation and extreme temperature variations. If microorganisms are in internal microcracks, they may be more protected than we imagine. This does not guarantee survival, but it creates a possible window. Panspermia does not require it to be common. It only needs to happen once, in billions of years, to change the biological history of an entire planet. Another obstacle is arrival. During atmospheric re-entry, the surface of the meteorite heats up intensely. However, studies show that the interior can remain relatively cool for a few seconds, depending on the size of the rock. The capsule burns on the outside but can protect on the inside. Therefore, Mars plays a central role in this hypothesis. It had liquid water in the past, a denser atmosphere, and suffered intense impacts. If life originated first on Mars, it could have been transferred to Earth when both planets were still young. This characterizes the so-called interplanetary panspermia. It does not involve distant stars, only cosmic neighbors. In physical terms, it is much more plausible than interstellar travel. The primitive Earth was unstable. Frequent impacts, intense volcanism, and oceans forming. It is possible that local chemistry was constantly disrupted. The arrival of external biological material at specific moments could have accelerated the process. Once established, life does not need much. It just needs to survive, reproduce, and compete. Evolution takes care of the rest. Billions of years later, we have the diversity we see today. All of this does not prove that panspermia occurred, but it shows that it does not violate known laws of physics or biology. It remains a bold, partially plausible, and profoundly transformative hypothesis. Panspermia does not solve the final mystery of the origin of life. It merely shifts the question. If life came from outside, then we need to understand where it first originated. This is a fundamental limitation of the hypothesis, and science itself recognizes this clearly. Even so, panspermia profoundly changes the way we look at the universe. If life can travel, even if rarely, then it may be connecting worlds over time. Planets cease to be isolated islands and become part of a cosmic network of potential living matter. One of the biggest questions in astrobiology is whether life, when it arises, always follows the same path. If we find life outside of Earth with the same chemical and genetic basis, it will suggest a common origin or transfer. If it is completely different, it will indicate multiple independent origins. Tuesday plays a central role in this test. If we discover Martian biosignatures related to terrestrial life, the panspermia hypothesis will gain real strength. In this scenario, the question would shift from if it happened to when and how. Moons like Europa and Enceladus are also priority targets. They have liquid groundwater, energy, and active chemistry. If life exists there, we will need to assess whether it originated locally or shares a relationship with life on Earth. Missions that bring samples of asteroids and comets expand our understanding of the chemistry of the solar system. Each analyzed grain reveals how the boundary between chemistry and biology can be gradual. The more complex the compounds found, the more plausible chemical panspermia becomes. The search for intelligent life also enters into this equation. If life is common, civilizations can arise in different places and times. Panspermia does not explain intelligence, but it may explain how simple life spreads, creating multiple starting points for evolution. There is a profound philosophical impact in this idea. If life is not exclusive to Earth, our history ceases to be central and becomes contextual. We are not the starting point, but a chapter. This may be uncomfortable, but it is also liberating. Life doesn't have to be grand to be meaningful. Even simple shapes represent organization against chaos. Panspermia invites us to see life as a persistent process that takes advantage of opportunities whenever physics allows. All the complexity we see today may have arisen from a minimal beginning. Whether local or imported, the central point is that life evolves, diversifies, and adapts. Panspermia does not diminish this process. It places it on a larger scale. Meteorites, comets, and dust cease to be just space debris. They become possible bearers of chemical history. Panspermia changes the meaning of these silent journeys through space. The elements that make up your body were born in stars. This is already a scientific fact. Panspermia merely asks whether, in addition to the elements, organized chemical patterns also traveled before becoming alive. If the answer is yes, our origin is a slow, unlikely, and extraordinary journey. If not, our origin is an equally extraordinary local emergence. In both cases, the result is the same. Life is a rare phenomenon in meaning, even if common in statistics. The science has not yet closed this case. There are clues, experiments, and partial evidence, but no definitive proof. Maybe we are right in the middle of the story, putting together a puzzle without yet seeing the complete picture. When we look at the sky, we don't just see distance, we see possibility. We see a cosmic file that may contain parts of our own origin. Panspermia brings the life of the universe closer to the universe of life. In the end, it matters little where life began. What matters is that it exists, persists, and tries to understand itself. Whether born here or arrived from afar, the mystery remains equally grand. If life can travel, the final question remains open. What else is still on the way? If this mystery captivates you, follow us.